Okay, we're on 6.5 non-metal and metal oxides in water. Let's take a look at the warm-up. It says, recall some of the information about chemical bonding that you have studied. Consider the electronegativity values of the main group elements in groups 1 and 2 and 13 through 17 as shown in the chart below. Number 1A, elements from which two of these 7 groups will form the most ionic oxides? Will it have to be groups 1 to 17? Because their electronegativity differences are the greatest. B, in which region of the periodic table are elements located that will form the most covalent oxides? This is the upper right region. And that's because the closer an element is to oxygen, the smaller the difference in electronegativity between that element and oxygen. Question number 2, consider the chemical equations below representing the typical reaction of 2 different oxide compounds with water. So I have sodium oxide and sulfur trioxide reacting with water. Determine the type of chemical bonds in each of the reactant oxide compounds and complete the following general statements. Well, Na2O, this is a metal with a nonmetal or a cation with an anion, so this would have to be ionic. And then sulfur trioxide, this is a molecular compound. You've got sulfur and oxygen both being nonmetals. So you could say that this is a molecular or compound which would have covalent bonds inside of it. So in general, the reaction of ionic oxides with water will produce basic solutions because here you have sodium hydroxide as a product. B, in general, the reaction of covalent oxides with water will produce acidic solutions. This is H2SO4. This is an acid that releases hydrogen ions into solution. So let's go on to basic anhydrides here. For basic anhydrides, in general, metal oxides are going to react with water to form bases. That's on the next page. Let's just take this over here. Metal oxides react with water to form bases, and non-metal oxides react with water to form acids. Now, there are some exceptions. For a metal oxide to react with water to produce a basic solution, it has to be both a highly ionic and soluble substance. Okay, this is only met by certain oxides formed from group 1 alkali earth metals and all but one from group 2 alkaline earth metals. So this would be beryllium, which is excluded. Metal oxides that react with water this way are called basic anhydrides. Anhydride means without water. So metal oxides form from the group 1 alkaline metals and the group 2 alkaline earth metals, except beryllium, react with water to produce basic solutions, and these oxides are referred to as basic anhydrides. When basic anhydrides react with water, the metal ions are typically spectator ions, so it's really the dissociated oxide that's going to react with water. So if you take a look, here, if you locate the oxide ion on the table of the relative strengths of the Bronsted-Lowry acids and bases, it's got all the Ka values. It's also in the very back of your book, it's table A5. You'll see that on the bottom right corner of the table, they've identified it as a strong base. So it has an enormous attraction for protons. So each oxide ion in water will actually remove a hydrogen or a proton from a water molecule. And then it converts to a hydroxide ion, and you can see that here. Here you have your dissociated oxide ion, and it's reacting with water. It actually pulls one of those hydrogens or protons from water, and you're going to get 2 hydroxide ions, which makes this very basic. Okay, so it converts itself to a hydroxide, and it converts a water to hydroxide. Now, not all metal oxides are considered to be basic anhydrides. Metal oxides are solids at room temperature, and a lot of them are not going to be soluble in water. There are several metal oxides, however, that are called amphoteric. If you're amphoteric, it means you can act as either an acidic oxide or basic oxide. Some examples would be beryllium oxide, Cr2O3, Al2O3, Ga2O3, SnO2, and PbO2. Some transition metal oxides that have a really high oxidation number are acidic oxides. Okay, so these are going to be things like manganese 7 oxide, which is right here, or chromium 6 oxide, which is right here. You'll notice that they actually react with water to produce an acid. Let's take a look at the quick check on the next page. What 2 criteria must be met for a metal oxide to be considered a basic anhydride? Well, the metal oxide must be highly ionic, and it has to be soluble in water. Which 2 families in the periodic table contain elements that satisfy these criteria? That would be elements that are in groups 1 and 2, except beryllium. Number 3, calcium oxide or quicklime is a component of dry Portland cement, which when mixed with water will eventually harden into concrete. Explain why continual contact of your hands with fresh Portland cement can lead to irritation. Well, the calcium oxide that's in cement is a basic anhydride. So it reacts with moisture in your skin. So it's going to produce hydroxide ions, and that strong base is going to be corrosive, and it's going to irritate your skin. Okay. Let's talk about acidic anhydrides. Okay, non-metal oxides that react with water are called acidic anhydrides. And when you have a reaction like this, no oxide ions are released into water, and no hydroxide ions are produced. The water molecule is actually going to bind to the molecular oxide, and you're going to form a molecular acid. So we can see that happening here. SO3 is my molecular oxide. Water is going to bind to it. I get H2SO4. this is my molecular acid. Okay. Then we've got down here, we've got an acidic anhydride that is normally going to contain a nonmetal with a really high oxidation state. So things like SO3, N2O5, or Cl2O7. So N2O5 is an acidic anhydride. And it's got nonmetals with really high oxidation states. And generally speaking, molecules that have at least 2 oxygen atoms per nonmetal are going to be these acidic anhydrides. So nonmetal oxides will react with water. They'll produce acids like here. I've got nitric acid. And that's why N2O5 is considered an acidic anhydride. So earlier we talked about how there were several metal oxides that could react with water to produce acidic solutions, but no non-metal oxides reacted with water to produce basic solutions. So let's take a look at carbon dioxide and water reacting to produce carbonic acid, which is a weak acid that's really, really unstable. So if you take a look here, if you've got a solution with carbon dioxide in different quantities, you're going to end up getting a bicarbonate ion and a hydronium ion, so you will end up getting a slightly acidic solution, and this is why pure water gradually becomes acidic when it's exposed to air. The carbon dioxide reacts with the water, you get hydronium ions, and it becomes slightly acidic with about a pH of 5.6. There is a trend on the periodic table that predicts some of the acid-base properties of some of the oxides. These are only for the main group elements. In general, as elements become less metallic, their oxides that react with water produce more acidic solutions. Remember, metallic character increases to the left and down as you move away from the nonmetals. So if it's becoming less metallic, you're going up and to the right. So it says here, this occurs as we move both left and right across the chemical period and bottom to top of a chemical family. Take a look at the quick check. It says a student adds a few drops of universal indicator to a small beaker of pure water and sees the expected pale green color indicating a pH of slightly less than 7. She then repeatedly blows exhaled air through a straw into a solution and notices the green color slowly change to yellow and then to pale orange. Explain the results. Well, the exhaled breath has carbon dioxide. And that carbon dioxide is going to react with the water in the beaker, forming a hydronium ion, which is going to make it more acidic. So as the pH lowers, the universal indicator changes color. Why are no hydroxide ions formed when covalent oxides react with water? Well, no oxide ions are released into water during hydrolysis. Let's go to practice problem 6.5.1 on the next page. Complete and balance the following formula equations. So here you've got a group 1 metal oxide reacting with water. you're going to produce a basic solution, potassium hydroxide, put a 2 in front of it to balance it. Here I have magnesium oxide. This is a group 2A metal, or group 2 metal oxide. Here you're going to make another basic solution. This would be magnesium hydroxide. Number 2, each of the following third period oxides reacts with water to produce acids. Arrange these oxides in order from least acidic to most acidic. Okay, well, we would probably have this being the most and this being the least. So we can automatically put Al2O3 first, Cl2O7 last, and then within there we're going to have SO3 here, P4O10 here, and SiO2 here. B, 2 of the above oxides react with water to produce strong acids. Write the balanced equations for those reactions below. Well, this is going to end up being Cl2O7 and SO3. So Cl2O7 reacting with water is going to produce perchloric acid, and then SO3 is going to react with water to produce sulfuric acid. Question number 3. Complete the following statements using either ionic or molecular in the blank spaces. In general, ionic oxides react with water to produce ionic bases, and molecular oxides react with water to produce acids. Acids are molecular compounds. Okay, now we're on the problem of acid rain. So one of the most widespread and serious problems of acid rain is in the form of rain, snow, fog, and even particle deposits. Normal rainwater has a pH of about 5.6. The pH, that's because carbon dioxide in the atmosphere is dissolved in it. If the pH is below 5.3, you have something called acid rain. Virtually all of the acid rain can be traced back to burning fossil fuels in vehicles or power plants or homes, and processing of mineral ores, We're on the human causes of acid rain. The major substances responsible for acid rain are gases that react with water. So each is a non-metal oxide that reacts with water to produce acid. Let's talk about some of the sources of some of the gaseous substances that cause acids to come out of the atmosphere. So some of the sources of sulfur oxides would be coal and oil deposits that contain sulfur impurities. When electrical power plants burn these fossil fuels, the sulfur is oxidized to SO2. Another source for sulfur dioxide is smelting. Smelting is when you extract metals from their ores by heating them. The first step is where you're actually roasting, and that's where the sulfides are heated at really high temperatures in the air, and you're going to end up producing sulfur dioxide. And the weak acid produced from the reaction of sulfur dioxide and water is called sulfurous acid, and it's really unstable, and it's not going to exist in molecular form in water, but you can see it here. Okay, and so this means that rainwater that's falling through sulfur dioxide in the gaseous state will end up being more acidic than normal once it hits the ground. And then, let's move this up. When air becomes even more polluted and it contains ozone and some fine dust particles, and if you've got some sunlight available, the oxygen and the ozone are actually going to oxidize some of the SO2 and SO3, and it's going to react with water to form a really strong acid known as sulfuric acid. Okay? So since strong acids like sulfuric acid are 100% ionized, that means you're going to have a high concentration of hydrogen ions or hydronium ions in the rainwater, and that will end up sort of wreaking havoc on the environment. Let's talk about the sources of nitrogen oxides. So the air is made up of 79% nitrogen and about 21% oxygen. These two gases react, they will not react typically because the activation energy is so high. But if we mix it with fossil fuels and we burn it in the internal combustion of a vehicle or an electric power plant, the high temperature and pressure is going to actually make those two gases react together. And when it reacts together, you're going to end up getting nitrogen monoxide gas. So nitrogen monoxide gas, when it encounters the cooler outside air, it reacts with oxygen and it produces nitrogen dioxide. And NO and NO2 are often referred to as NOx. So nitrogen dioxide reacts with water. You end up getting a strong acid, nitric acid, and then you get a weaker acid, nitrous acid. Okay? So let's turn the page, and a summary of the cause and effect of acid rain are given here. You've got SO2 and NO2 coming out of this plant. The pollutants move through the atmosphere and then into the cloud water, and then it rains down, and it kind of destroys plants, animals, pollutes rivers, streams, and it can erode stone. Let's take a look at the quick check. Identify the 3 non-metal oxides that react with water in the atmosphere to produce acid rain. Well, this would be NO2, SO2, and SO3. How do coal-burning electrical power plants produce the sulfur oxide responsible for acid rain? When they combust impure coal that contains pyrite, it produces SO2. So combusting impure coal containing pyrite, bless you, produces SO2. So this would be something like FeS2 plus oxygen will produce Fe2O3 and SO2. Why can the problem of sulfur oxide acid rain become worse in polluted air? Because the polluted air if it contains ozone and fine dust and some sunlight, the oxygen and the ozone will oxidize some of the sulfur dioxide and sulfur trioxide. So oxygen and ozone oxidize some SO2 and SO3. Let's talk about the consequences of acid rain. So Scandinavia receives acid rain from Germany, England, and countries in Eastern Europe. Southern Ontario and Quebec in Canada receive acid rain that originated anywhere in the U.S., typically between Chicago and Boston, because that's kind of an industrial belt. Rainwater with a pH of 7, which is really close to vinegar, has been recorded in Sweden, and a pH of 1.8, which is just about the pH of stomach acid, has been recorded from rain in West Virginia. Aquatic and terrestrial ecosystems can be severely affected when they're exposed to acidic conditions. Most fish die at a pH below 5. And entire forests have been devastated by acid rain. The soils contain aluminum salts, which are typically not soluble in groundwater, but they begin to dissolve with more acidic conditions. So if they end up dissolving, we release these aluminum ions into the soil, which are toxic to fish, and they leach out a lot of the nutrients that are valuable to soil. Take a look here. Here's some of the acid rain damage. You've got buildings, monuments, cemetery headstones. Since they contain marble or limestone, the carbonate salts dissolve in acids. You'll have damages to structures. You'll have trees and soil and water and fish damaged by acid rain. This is a statue showing you the damage from exposure to acid rain. There are some reasons for optimism, though. Some of the lakes are naturally protected because they're bounded by soils that are rich in limestone. Limestone actually dissolves the hydronium ions from acid rain, and you end up getting more bicarbonate ions. And as the bicarbonate ion concentration increases, the lakes actually become a buffer. And so it maintains a relatively constant pH. A temporary solution would be add calcium carbonate or calcium oxide directly to a lake. There are some strict emission standards on automobile manufacturers to produce cleaner and more efficient vehicles. One of them is the catalytic converter, which reduces carbon monoxide and unburned hydrocarbons and nitrogen oxides released into the air. Most of the major car companies have produced hybrid vehicles. They use two power sources. The most common would be a hybrid electric vehicle or an HEV, where they combine a combustion engine with an electric motor. If you turn the page, there are two electric vehicles. One is the Volt, another one is Leaf. A method for removing sulfur dioxide gas from a coal-fired power plant would be, or a metal smelter would be something called scrubbing. This is where they blow powdered limestone into a combustion chamber. The heat decomposes it to calcium oxide and carbon dioxide gas. And the calcium oxide, which is lime, is going to combine with sulfur dioxide to produce solid calcium sulfite. To remove the calcium sulfite and any unreacted sulfur dioxide, they're going to spray calcium oxide into the exhaust gas before it reaches the smokestack, and it produces a thick suspension of calcium sulfite called a slurry. It's really, really expensive, though. It takes a lot of energy. And they end up burying some of the excess compounds in landfills.